So first, we're going to start off with our functions that we need to import, such as making the integrations and subplots in order to carry out all the computations. And so the first part of the problem is going to be showing us how to get from this dehydrogenization of ethanol, and we're going to be producing the acetaldehyde and hydrogen. And so at the very beginning, there is that mole fraction. It's going to be a 1 to 1 to 1, and it's all going to be in the gaseous phase. And for this problem, we also have the diffusion coefficients in the meters squared per second for D1(2), D1(3), D2(3). We also have the given constants in the problem as well, such as pressure, temperature, and the R constant that is just given to us just as we know, as well as the film thickness, we'll call delta. Next, what we have going on is the concentration calculation. So it's going to be a variation of PV equals nRT, where N over V is going to be left over on one side, therefore showing concentration. And then next we have the initial concentrations over here with the 60% ethanol, 20% acetaldehyde, and then 20% hydrogen. But to get that hydrogen calculation, you just take 1 minus the ethanol minus the acetaldehyde, which is just 1 minus 0.8, and therefore 0.2. And then we also have our initial guess as well to help us in this. Okay, so for the next part of the code, what we're going to be doing is solving the mole fractions with the molar flux at the delta point. However, what we would need to be doing is solving these simultaneously, so we're running these equations down here. And then for this first part up here, these are essentially the bootstrap relations that we use to determine from the little stoichiometric equation, right? So it's going to be 1 to 1 to 1 ratio, or if you're on this left side over here, this will be a positive, and these two would be negative 1 to 1, or it could be vice versa. This one would be negative, and these would be positive 1 to 1. So that's just all putting it into a relation there. We also have the 10 as the rate constant. That'll be 10 moles per meter second squared. So that's also included. Next, we have the Stefan-Maxwell equations, and that's just going on over here, initializing those variables. And then additionally, we have these equations down here in order to solve these variables and these values. What you could do is, say for N2 or N3 over here, you could set those as negative N1 or positive N1, again, how the question is being framed. But just as you know, as a precaution, just make sure everything is here present in the equation. It can be good to have N2, N3, so that way you know you're getting each of these different variables all accounted for. Okay, so for this next little area down here, what we're going to be doing is solving these differential equations from above. And to do that, we're going to be determining mole fractions from the relation to the mole flux. And to do that, we are integrating from 0 to 1, and then we're going to be using the y1 naught, y2 naught, and then y3 naught will be present through the above method of taking 1 as the whole fraction subtracted by y naught, or y1 and y2. And down here in this section of the code, we're going to be saying how we're solving this continuously, and all the values are going to be updated. And then okay, so for the next, we're going to be using the root function, and it's essentially going to be used to reach 0 while using the initial guess up here. So whatever we put in the beginning, that's going to be used down here to help get things in motion. And then again, because we're going to be using these solve the IVP, what we're going to be doing is that we're going to keep reusing the same equation, and it'll essentially be a loop until we get it close enough to get a good idea what's going to be going on. And with that, if we're going to be solving it and putting it into a number form, we'd use this code down here, which is be 0.88, or if you were to use the graph that we're going to be talking about here soon, you'd just be taking that 0.088, and then you're going to be putting that inside the... So next in the code, we're going to be using the root function, and that's going to be attempting to reach 0 while using the initial guess in the beginning, and which in this case would be 0.01, and that's just here to kick things off. You know, and then this next card or part of the code is just be running a couple loops in order to get down to the desired value where everything is just balancing out with each other. So that's going to be that code right there. It's going to be similar to the one as previous, except the argument answer is going to be using that answer up here rather than y1d that we were using up here. Okay, so next what we're going to be doing is helping out the graph to get all organized and nice. We're going to be using the eta as a variable in order to show how far along the film thickness it is, and to help things look nice. We're going to be going from 0 to 11, and we're going to be going increments of 1. That z value is going to be the delta value that we have at the very beginning over here, 1 e to the negative 3 meters. Yeah, so that'll just be showing in actual value terms what's going to be going on here. And this y1 and the y2 values are going to be using that eta variable in order to, again, make things look nice. So it's going to be plugged into those previous equations that we solved in order to get the values on the axes of the graph. Okay, and then finally we're going to be making the graph itself with this piece of code. So y1, y2, it's just going to be using those values that we plugged in with the eta. Those are pretty simple. And then the y3, again, we said that we were going to take it by taking 1 minus y1 minus y2. That'll again be y3. And over here, we're just going to be setting things out. So it would be 500 by 500 width and height, how big the plot's going to be, some preferences, how the plot looks, title, axis title, and then again, so these are going to be mole fractions with position here in meters, the actual mole fractions over out of 1. And again, going down here, we can find out N1 by just using that piece of code. Or again, you can use it at the interface, taking that 0.088 times 10. And then finally, to interpret the graph a little bit, when we're starting here at the position 0, we have those initial mole fractions. However, as you see, as we're increasing along the film thickness, our fractions are going to be increasing for both y3 and y2, which again were going to be the acetaldehyde and hydrogen. And in y1, where it was initially 0.6, it's going to drop all the way down to that 0.08 that we were talking about before. So yeah, as the driving force is moving the things along, the y1 is going to be decreasing until you get to that boundary layer, and then y2 and y3 just be increasing.